Okay, so the paper is called Sparsely Aggregated Convolutional Networks, and I actually really like it. It's one of those papers that has a super simple idea and it totally makes sense. At least the intuition totally makes sense. We'll see if the results work out. Um, the authors are basically proposing a new type of architecture structure. And the idea is that instead of using ResNet or DenseNet blocks, they aggregate the outputs of a sparse subset, sparse subset of the previous layers. And this will yield better performance with fewer parameters. So let me explain a little bit in more detail. So first, a little bit of background. Everything is going to be built on skip connections. So skip connections were introduced with ResNets, and the idea is that instead of just feeding an image through a series of layers, as in VGG, where you have like a conv layer, then a ReLU, then a batch norm, maybe a pooling layer, and you just feed it through, you actually add the previous layer output, or more precisely, the inputs of your current conv ReLU / batch norm group together with the output. So mathematically, like if YT would be a layer and F would be a series of conv, ReLU, and batch norm layers, you would be saying that YT, so the next activations are equal to like this function of the previous activations plus the previous activations. And in the case of DenseNets, it's not a plus, but it's a concatenation. Now, the authors of this paper point out that actually you can write this expression equivalently. Actually, can you guys see my mouse? Maybe this is better. Oops. So you can write this expression equivalently as the outputs of your previous layer plus, and then you just express by t minus 1 as f of yt minus 2 plus yt minus 3, and you express f of yt minus 3 as f of yt minus 4, and so on. So you basically just like expand all of this expression, and that's basically just a sum over all the outputs of all the preceding layers. So visually, you can visualize a ResNet as basically combining at every stage your current outputs with your inputs, or you could expand this expression and say, well, this is actually my current output combined with the previous output and the output before that and the output before that, and so on. And exactly the same is true for DenseNets, except in the case of DenseNets, it's a concatenation. Now, skip connections have a couple of benefits. Number one is that they stabilize training. And the reason for that is that the distance between your early layers and your loss is much smaller, which means the gradients can pass through much quicker and update the early layers more effectively. So imagine your losses here. Then with the skip connections, actually the effective distance between your loss and your first layer is just 1. Versus if you didn't have the skip connections, in this example, it would be 8 layers. So that's benefit number 1. Benefit number 2, and this is especially true of DenseNets, is that you don't have to reuse features that you've already computed. So you can, whoever that is, can you turn off your mic? Okay, so you don't have to recompute features. You can just leverage the features that you've already computed. And this is especially true of DenseNets because in the case of concatenation, you basically retain all the information of the previous layers. Now, that being said, there are some drawbacks to this dense aggregation structure. And the drawbacks are actually different for ResNets and dense nets. They're kind of polar opposites. So in the case of ResNets, we are over constraining the model. So this kind of sum is not going to be very flexible. And the authors point out that that's the reason why ResNets saturate at some point. So at some point, adding extra layers to a ResNet just doesn't improve performance. Now, they mentioned this at a very high number of layers, like 1,000 layers. I don't think any one of us is actually training that deep of a ResNet, but it's still a drawback, right? You can't really scale it up effectively. And ResNets have an additional drawback to dense nets, which is that they have to recompute some features if you need to reuse features as you move forward in the network. Dense nets, where you concatenate aggregations, suffer from the exact opposite drawback in that you are overburdening the system. Your parameters go quadratically with the depth of the network. So if you have n layers, then your parameters will be proportional to n squared. So you'll have too many parameters. So instead of this structure, the authors propose this sparse segregation. So instead of basically summing or concatenating the outputs of all the previous layers, we just concatenate a sparse subset of them. They actually focus more on the denseNet part rather than the ResNets part, I think because denseNets are, generally speaking, more parameter efficient. So most of their comparisons are relative to denseNets. So they will be using concatenation as their operation. And so they concatenate the outputs of a sparse subset of previous outputs. Specifically, they use exponential offset. So they use the previous layer, the layer before that, then 4 layers before that, then 8 layers before that, and so on. So here is just a different visual representation. So if I is your current layer, then instead of summing or concatenating all the previous layers, you just concatenate layers with an exponential offset. And this table gives a rough overview of what this means for parameters or the shortest gradient path. So for a plane network, as in VGG with no skip connections at all, your parameters are proportional to the depth of the network, and the path from the loss to your first layer is again proportional to the network size. With ResNets, you have the same linear growth in parameters, but your shortest gradient is just a constant. In fact, it's 1. And then with densenets, this is n squared. And the model they propose with concatenation, concatenating these sparse previous layers would then have a parameter growth rate of n log n and the shortest gradient path of n log n. Now, they actually present a lot of results on SciPar 10, SciPar 100, ImageNet. All the results share a common theme, which is that if you replace denseNet with the sparseNet of the same structure, you get somewhat equivalent errors, maybe a little bit worse errors, but with much fewer parameters. And then equivalently, if you have the same parameters for, let's say, dense nets or sparse nets, then you get much better results. And the same is true for dense. So for example, just as an example here, DenseNet 121 would have a 25% top one error rate on ImageNet, has about 8 million parameters. The same network, except with sparse aggregation, has a slightly worse error, but it has almost half the number of parameters. And if we compare networks with about the same number of parameters, so let's say this one has 8, this one has 7, so actually less parameters, then the sparse net wins out. So basically, obviously, since you have less parameters with a given number of layers, you can increase the number of layers to achieve the same number of parameters. And this is pretty much the same instead presented visually. So the left graph is on CIFAR 10, or maybe CIFAR 100. I'm not quite, I think it's CIFAR 100, looking at the error rates. And the right graph is on ImageNet. And yeah, it's basically plotting the number of parameters and the validation error. And it's pretty clear that you can achieve the same performance with much fewer parameters with this sparse aggregation structure. It's a little bit less clear once you like get to the once you get to like these very basic networks, whether it makes much of a difference, but like as you scale up the networks, it's definitely seems to matter a lot whether you aggregate densely or sparsely. Another drawback with dense nets is that they actually contain redundant features. And by that, I mean the following. You can plot the average activation in a given layer relative to, sorry, you can plot the absolute size of the weights in a given layer relative to the previous layer's aggregation, relative to the previous layer's activations, since you concatenate them all. And what you find is that you mostly use the current layer, i.e. the diagonal, maybe like the previous layer or the layer before that, but like eventually the features you learn are going to be kind of useless. Like you don't really use them with much weight. And that's why as you like go look from layer 10 to the absolute size of your weights, they gradually decrease. And the sparse representation doesn't really have this same problem because you actually only retain a few early layers, and in fact, you increase the distance of the retained layers exponentially. So you pretty much always use the features from your early layers, which is good because it means that your your network doesn't have redundant features, which means you can reduce your parameters. And then I created my own test runs. So the authors have their own code on GitHub. They have a TensorFlow version and the PyTorch version. I don't know about the TensorFlow version, but the PyTorch version is actually not that good in that it's hard to make apples to apples comparisons to like the regular fast AI models because there are always like some tiny differences that are off. And second, even the usual dense nets seem to take a lot longer to train in their implementation versus the regular, let's say, fast AI PyTorch implementations. And I think that's because they don't structure their code very well. Also, their main results are the TensorFlow results, so this might not be applicable to those at all. But as far as the PyTorch version is concerned, it's not quite ready to use yet. So what I did here in this plot is the following. I first fitted a PyTorch ResNet and PyTorch DenseNet model. So that's the blue and the yellow curve here. All models were fitted for 10 epochs, and I recorded the time it took me to fit these models and what accuracy I obtained with them. And then I fitted the author's implementation of DenseNet. They didn't quite have the equivalent one, so I made a configuration that has about the same number of parameters, but as you can see, it took a lot longer to train. It eventually achieves a very good performance, but it just took way longer to train, and it's not apples to apples comparison. And then I trained their SparseNet implementation, which is much quicker. So, yep. Okay. So if like this kind of pattern generalizes and there is going to be a better standard implementation of their idea out there, then I think it could be really useful, because it would basically not just allow you to train very deep networks, but also cut back on your training time. And you know, this might even have applications to platform, even though we don't use a DenseNet, we use a ResNet. I mean, ResNets don't quite suffer from the same problems, but DenseNets have other advantages as well. For example, the concatenation would allow platform to just like retain the last layer activations, because it already contains all the previous ones, or a sparse subset of the previous ones, and you wouldn't need to inspect 5 separate layers to do your projections, for example. But in that case, actually like adding this like sparse structure would potentially even make it better, because again, you have about the same performance for much fewer parameters. All right, so any questions? All right, well, I guess that's it then. Oh, okay, yeah.
Hi, Kristen, how are you?
Yeah, I'm good. So results slides.
Let's see. Oh, that's not my question.
Oh, okay. Yeah, anyway, go ahead, David, and then, or who's asking, actually?
My name is Nasser.
Okay.
Okay, yeah.
Nice to
So,
meet you.
yeah, nice to meet you too. So, my question, I read the paper, but like if you can go back to the slide that shows the architecture of the SparseNet. Yeah, this one.
Yep.
So I was wondering how they came up with this architecture. For instance, the output of F0 is connected all the way to F8, and then it's connected to input of F2. But so how do they know that how do they know to connect the output of which layer to which layer in this case?
Okay, so they basically hard-coded it in. So if you're wondering, well, you know, why is it an exponential offset? Why not something else? Well, it's just like the one thing they tried, or maybe they tried multiple things, I don't know. But I mean, the intuition of their idea is the following. You don't want to connect your current outputs to all previous outputs, as in like dense aggregation structures, like for ResNets or DenseNets, because that suffers from a couple of problems. But you also want to retain the benefits of skip connections, mainly the feature reuse and the fact that it stabilizes training. So you want to only connect your current layer to a subset of the previous layers. Now the question is, what subset do you connect it to? Well, obviously, it should be centered around the nearby layers. So obviously, you want the previous layer, and then maybe the one before that. And from very early layers, maybe you want a couple because you still want to obtain like these lower level features that the network takes up, but you don't want all of those layers. Mm-hmm. So now you just look for a convenient functional representation of that, and an exponential offset is such a convenient representation. Now, right. If the question is, well, could you tweak it? Could you make it even better? And maybe you can. I don't know. Maybe some other kind of offsets would work even better. But I think it's more important to focus on the intuition, which is that you want to connect your current layer to previous layers, like at skip connections, but you don't want to do this for all the previous layers. You want to do it for a subset of them. And now now the whole question is, how do you choose that subset? Does that make sense?
Yeah, totally, yeah. So the intuition is more important than like the architecture of how the offsets are connected together, right?
Yeah, exactly. And as I mentioned, I don't quite like their current implementation. It's relatively slow, even for normal architectures. So all of that needs to be refined. But I think the intuition is actually correct. Like, okay. Yeah.
Thank you.
You're welcome. Anyone else? Let's see the chat. David? Anything from the results slides? This one or this one? Not sure. Res Next. I don't think they made any comparisons to Res Next. In fact, I don't know what Res Next is. Okay, does it have like a similar concept behind it? It performs a bit better. Okay, but is it like a similar tweak as in here? Like, do they tweak the actual architecture structure? Because I mean, if not, then you can imagine that this idea could be implemented in that setting as well. Yep. All right, any other questions? All right. Well, see you all then.